Humanity has now confirmed the existence of over 5,500 exoplanets. The search for life beyond our solar system is no longer a theoretical pursuit, but an active observational science. Much of this progress is driven by the James Webb Space Telescope. Its design allows it to capture the faint light filtering through these distant atmospheres, revealing chemical components that were previously invisible to us. However, this hardware has created a logistical hurdle. Modern observatories generate thousands of these atmospheric readouts, known as spectra, creating a volume of information that human scientists cannot process manually. Sorting through this volume of spectral information is a task beyond human bandwidth. The current bottleneck in the search for life isn't the quality of our telescopes, but the speed of our data processing pipelines. Historically, extracting meaning from the variations in an exoplanet's starlight relied on traditional Bayesian forward modeling, a method where astronomers manually simulate thousands of potential planetary conditions to see which one best matches the observed data. This dense matrix of correlation plots illustrates the mathematical burden of that traditional approach. Decoding the complex probabilities hidden in a single planet's dataset this way can take days, even with immense computational power, making it difficult to scale for missions involving hundreds of targets. This diagram maps out a faster alternative: Convolutional Neural Networks, or CNNs. By using this specific artificial intelligence architecture, scientists replace slow modeling bottlenecks with rapid machine learning pipelines. To build these models, scientists train the network on thousands of synthetic atmospheres. They inject realistic Gaussian noise into the data, teaching the AI to identify specific chemical fingerprints even when the signal is heavily distorted. This technological shift accelerates the detection process, flagging potential biosignatures in a fraction of the time and allowing researchers to prioritize the most promising targets for further study. The practical application of this technology was demonstrated in 2023 with K2-18b. It is a sub-Neptune exoplanet located 120 light-years away, orbiting within its star's habitable zone. Based on its mass and radius, scientists suspect K2-18b might be a Hycean world, a planet characterized by a thick, hydrogen-rich atmosphere covering a massive liquid water ocean. When automated pipelines analyzed the light passing through that atmosphere, they identified high concentrations of both methane and carbon dioxide. But the data flagged another specific signature: dimethyl sulfide, or DMS. On Earth, this chemical compound is exclusively produced by living organisms, primarily marine phytoplankton. If follow-up observations confirm this DMS signal, it proves that AI can successfully flag the subtle, complex chemical patterns that indicate active biological processes. To find something like DMS, the AI relies on the physics of transmission spectroscopy. As starlight passes through a transiting planet's atmosphere, specific chemical compounds absorb specific wavelengths of light. Carbon dioxide, for instance, absorbs light at exactly 2.7 micrometers. Because those specific wavelengths are absorbed, they are missing from the light that eventually reaches our instruments. This creates a sequence of dips in the spectrum, effectively forming a planetary barcode. But telescopes do not output a clean barcode. This jagged line plot shows the reality: raw, noisy spectral data filled with volatile spikes and large error bars. The CNN handles this by converting the noisy graph into a 2D image. This allows the AI to compare the visual pattern against millions of known chemical models in an instant. To ensure the result is accurate, the network extracts features from multiple wavelength bands simultaneously. By confirming absorption across different parts of the spectrum, it eliminates false positives caused by unrelated peaks. By reading these barcodes directly, the AI calculates the statistical probability of life-sustaining molecules in a fraction of a second, significantly outperforming manual methods. The tools being developed today are a pilot for the Habitable Worlds Observatory. Planned for the 2040s, this mission will search for signs of life on at least 25 Earth-like exoplanets. By extending our telescope's detection ranges into new infrared and ultraviolet wavelengths, we will provide AI models with the data needed to identify much more complex organic molecules. Future AI will also move beyond simple data processing. These networks will eventually prioritize targets autonomously, instructing telescopes where to look next based on real-time anomaly detection. The search for life is integrating these automated networks to manage the sheer volume of incoming cosmic data. When we finally get definitive confirmation that humanity is not alone, it will not come from a scientist peering through a glass lens. It will come from the quiet, mathematical alert of a machine.